Rare earth processing capabilities, China versus world. The global discourse surrounding critical minerals often fixates on the act of mining, the physical extraction of ore from the crust of the earth. This focus, while understandable given the visibility of open pits and massive haul trucks, fundamentally misunderstands the nature of the rare earth element supply chain. Mining is merely the prelude to the true industrial challenge: separation. The economic and strategic dominance of the People's Republic of China in this sector is not solely a function of geological endowment, nor is it merely a byproduct of lax environmental regulations, though both play a role. Rather, China's hegemony is a triumph of chemical engineering, process optimization, and state-directed industrial scaling that has created a technical efficiency gap so profound it constitutes a new form of asymmetric industrial power. For nearly 4 decades, Chinese state-owned enterprises, led by the behemoth China Northern Rare Earth Group High-Tech Co. Limited, have refined the hydrometallurgical processes required to separate the 17 chemically similar lanthanides with a precision and cost efficiency that Western competitors are only now beginning to approximate. This review provides an exhaustive comparative analysis of the operational realities defining the global rare earth supply chain. It moves beyond superficial market share statistics to interrogate the technical efficiency gap between established Chinese processing giants and the emerging Western ecosystem. By strictly examining the baseline solvent extraction efficiencies of Baotou against MP Materials and Linus, the management of feedstock complexity, the deployment of novel separation technologies, and the critical missing middle of metallization capacity, we can quantify the challenge facing the West. Furthermore, we analyze the specific geological advantage of southern China's ionic adsorption clays against Western heavy rare earth hard rock projects, revealing that the gap is not a singular void, but a complex series of technical, chemical, and economic asymmetries that defy simple solutions. The stakes of this technical divergence are existential for modern industrial economies. Rare earth elements are the vitamins of modern industry, essential in small quantities, but irreplaceable for the functionality of high-performance magnets in electric vehicle motors, wind turbine generators, and precision-guided munitions. The ability to separate these elements, to tear a neodymium atom away from a praseodymium atom when they are almost identical in ionic radius and chemical behavior, is the bottleneck through which the green energy transition must pass. As Western nations attempt to reconstruct this capability after decades of offshoring, they find themselves not just competing against low labor costs, but against a mature, scientifically advanced, and digitally optimized industrial machine. Baseline solvent extraction efficiency, the Northern Standard versus the Western ramp-up. The separation of rare earth elements relies primarily on solvent extraction, SX, a hydrometallurgical process where rare earths are transferred between immiscible aqueous, water-based, and organic, oil-based phases. The efficiency of this process, defined by separation factors, recovery rates, reagent consumption, and throughput, dictates the economic viability of a refinery. It is here in the vast mixer-settler Cascades of Inner Mongolia that the baseline for global efficiency is set. The China Northern Rare Earth Group High-Tech Company Limited, operating out of Baotou in Inner Mongolia, sets the global benchmark for light rare earth element separation. The operational reality at Baotou is defined by its massive scale and the integration of the Bayan Obo deposit, the world's largest rare earth reserve. The technical efficiency of the Baotou operations is rooted in decades of iterative optimization of the saponification and extraction circuits, creating a system that is robust, flexible, and ruthlessly efficient. According to technical audits and research publications, the Baotou solvent extraction circuits achieve a neodymium-praseodymium recovery rate consistently exceeding 95%. Even more impressively, The purity levels for separated oxides routinely reach 99.5 weight% or higher, meeting the stringent requirements of downstream magnet manufacturers without the need for extensive reprocessing. This is achieved using established extractants, primarily P507, 2-ethylhexylphosphonic acid mono 2-ethylhexyl ester, and P204, di-2-ethylhexylphosphoric acid in kerosene diluents. While the chemistry of P507 and P204 is known globally, the operational mastery lies in the hydrodynamic stability of the mixer-settler cascades at Baotou. The extraction rate at these facilities is reported to be as high as 9.3 grams per hour per square meter, a metric that underscores the intensity of their throughput. This high throughput is not accidental. It is the result of engineering feed solutions with exceptionally high concentrations of rare earth elements, up to 46,000 milligrams per liter. Processing such concentrated solutions creates technical challenges, specifically in maintaining phase stability, preventing the formation of emulsions or crud that can clog the system, and ensuring selectivity. The Baotou operators have mastered the use of neutral extractants like TODGA in specific circuits to handle high acidity and concentration, allowing for smaller equipment footprints relative to output. This reduction in physical footprint per unit of production reduces capital intensity and improves the thermal efficiency of the plant as less energy is wasted heating vast volumes of dilute water. Furthermore, the Baotou circuits have been optimized to selectively extract high-value rare earths like neodymium, praseodymium, and dysprosium without significant co-extraction of non-REE impurities, such as iron, nickel, or aluminum, even when processing scrap magnets or complex concentrates. This selectivity is crucial because co-extracted impurities act as poisons in downstream electrolysis, increasing energy consumption and lowering metal quality. The ability of Northern Rare to feed dirty solutions into their SX circuits and still pull out 99.9% pure oxides is a testament to their command of the chemical equilibrium, a tolerance that Western plants, designed for specific, cleaner feedstocks, often lack. Against the mature, integrated operations of Baotou, MP Materials' Mountain Pass facility in California represents the vanguard of the American rare earth renaissance. The operational reality at Mountain Pass, however, is distinct from Baotou in both mineralogy and processing philosophy. The Mountain Pass ore body is a world-class bastnasite deposit with an average feed grade of approximately 8.7% rare earth oxide, REO. While this is a high grade by global standards, it presents specific beneficiation challenges that define the facility's efficiency profile. The primary efficiency challenge for MP Materials has historically been in the beneficiation stage, the physical upgrading of ore to concentrate before chemical separation even begins. Operations at Mountain Pass utilize a sophisticated flotation circuit to upgrade the 8.7% run-of-mine ore to a concentrate grading approximately 60% REO. The recovery rate of this flotation process is reported at approximately 72%, with beneficiation losses estimated at 10%. This implies that a significant portion of the rare earth value is lost to tailings before it ever reaches the solvent extraction circuit. While a 72% recovery is respectable in mineral processing, it contrasts with the highly integrated recovery systems in China, where tailings often undergo secondary scavenging or are reprocessed in auxiliary circuits to capture marginal value. In terms of cost efficiency, the operating cost per ton of REO at Mountain Pass was reported at approximately $1,430 in 2020. This figure, while competitive, reflects the realities of operating under strict environmental regulations in California, which necessitate a zero-discharge water facility and dry stack tailings management. MP Materials has made significant strides in operational efficiency, reporting record production volumes of 42,413 metric tons of REO in concentrate in 2021, and increasing NdPr production by 51% year-over-year by late 2025. The company operates a closed-loop reagent scheme, utilizing a chlor-alkali facility on-site to produce its own hydrochloric acid and sodium hydroxide reagents from brine waste. This vertical integration of reagent production is a strategic masterstroke, but also an operational burden. It shields MP Materials from volatile commodity chemical prices and logistics disruptions, but it adds a layer of technical complexity. Managing a chlor-alkali plant is an industry in itself that Chinese SOEs do not necessarily need to manage internally. The Chinese model relies on the externalization of certain ecosystem costs and the subsidized procurement of reagents from a massive domestic chemical industrial base. MP Materials must internalize these costs to maintain its cleanest rare earth producer branding, effectively paying a green premium on its operational expenditure that creates a structural cost floor higher than its Chinese counterparts. Lynas Rare Earths offers a third paradigm, one that balances high-grade Australian geology with Malaysian chemical processing. Sourcing from the Mount Weld carbonatite in Western Australia, a deposit with an exceptionally high grade of 14.8% REO, compared to the 8% found in major deposits like Mountain Pass or Bayan Obo, Lynas enjoys a natural head grade efficiency. Higher grade ore means less material must be moved, crushed, and ground to achieve the same output of REO, intrinsically lowering the energy intensity of the front-end mining and beneficiation operations. The Lynas flow sheet has historically relied on shipping concentrate to the Lynas Advanced Materials plant in Kuantan, Malaysia, for cracking, leaching, and solvent extraction. The efficiency of the Malaysian CX circuits is high, capable of producing separated NdPr and engaging in heavy rare earth separation. However, regulatory pressures regarding low-level radioactive waste in Malaysia have forced Lynas to construct a new cracking and leaching plant in Kalgoorlie, Australia. This shift represents a redundancy tax on efficiency. While the Chinese industry centralizes operations to maximize economies of scale, for example, the consolidation of the Big Six SOEs into even larger conglomerates, Lynas is effectively decentralizing its flow sheet to mitigate geopolitical and regulatory risk. The new Kalgoorlie facility processes the concentrate into a mixed rare earth carbonate, or MREC, which is then dried, packaged, and shipped to Malaysia for re-dissolution and separation. This adds a drying, packaging, shipping, and re-leaching step that does not exist in the integrated industrial parks of Baotou. While Lynas has achieved efficient operations, producing approximately 10,500 tons per annum of NdPr products, the structural necessity of maintaining a cross-ocean supply chain places a floor on their cost reduction potential. The Chinese SOE model, where the mine, the cracker, the separation plant, and often the metal furnace are located within the same industrial zone, eliminates these logistical frictions, granting them a structural efficiency advantage that Western companies, spanning jurisdictions to appease regulators, struggle to match. Feedstock complexity, the mixed ore challenge versus Chinese IP tolerance. One of the most profound but often overlooked differentiators in technical efficiency is the tolerance for feedstock complexity. Rare earth minerals rarely occur in pure forms. They are often chemically bound with radioactive elements like thorium and uranium, or locked in complex mineralogical matrices involving phosphates, carbonates, and silicates. The ability to process these messy ores efficiently is a key differentiator between Chinese and Western operations. The Bayan Obo deposit is chemically chaotic. It is not a pure bastnasite deposit like Mountain Pass. It contains a mixture of bastnasite, a fluorocarbonate, and monazite, a phosphate. Historically, processing mixed ores was considered inefficient due to the competing chemical requirements to crack both minerals. Bastnäsite releases fluorine, which corrodes equipment, while monazite requires aggressive cracking to release the rare earths from the phosphate lattice. However, Northern Rare Earth Group has turned this geological bug into a feature through the development of specialized caustic crack and acid roasting flow sheets. Chinese research and industrial application have perfected a sulfuric acid roasting process at temperatures exceeding 300 degrees Celsius to crack the monazite, followed by leaching to form rare earth sulfates. Alternatively, digestion in sodium hydroxide, NaOH, is used for monazite, followed by hydrochloric acid leaching. The crucial innovation is the IP tolerance, the intellectual property and operational know-how to handle the fluorine, phosphorus, and thorium emissions associated with this mixed processing. Chinese researchers have developed flow sheets that separate bastnäsite and monazite prior to leaching, or leach them sequentially to recover not just the rare earths, but also the thorium and fluorine as byproducts. For instance, complexing agents are used to dissolve bastnäsite while leaving monazite intact for separate treatment. This flexibility allows Baotou to accept a wide range of artisanal or third-party feeds, blending them into their massive circuits. They operate as a universal sink for rare earth concentrates, smoothing out mineralogical inconsistencies through sheer volume and chemical aggression. The scale of Baotou allows them to tolerate lower recovery rates on specific batches because the aggregate output is so massive and the byproduct credits, fluorine, fertilizers from phosphorus, offset the costs. In contrast, Western processors typically seek pure feedstocks to simplify their flow sheets and reduce technical and regulatory risk. MP Materials benefits from a bastnäsite-dominant ore, which allows for a streamlined acid leaching process similar to the Sichuan method, avoiding the intense radioactive management associated with monazite. However, this limits their ability to easily integrate heavy rare earth feeds from other sources without modifying their environmental permits and chemical circuits. Projects like Arafura's Nolan's Bohr, Apatite, and Chairolite, or Northern Minerals' Brown's Range, Xenotime, must develop bespoke flow sheets. Arafura, for example, has had to design a process that handles high phosphate levels up to 14% and manages thorium residues. The efficiency gap here is that every Western project is effectively a prototype, requiring years of piloting to validate a unique flow sheet, as seen with Rainbow Rare Earth's phosphogypsum process. Chinese SOEs utilize standardized, modularized mixer-settler designs that are robust enough to handle feedstock variability. They do not reinvent the wheel for every mine. They simply adjust the acid/flow ratios of their existing massive wheels. Furthermore, the West's aversion to RADS, radioactivity, creates a feedstock bottleneck. Monazite is rich in NdPr and heavy rare earths, but contains thorium. China views thorium increasingly as a potential resource for future molten salt nuclear reactors or a manageable waste stream. Western jurisdictions view it as a liability, requiring complex, expensive disposal solutions, effectively disqualifying vast amounts of potential feedstock from entering the Western supply chain unless it passes through a facility explicitly licensed for radioactive materials, such as the Energy Fuels White Mesa Mill. This regulatory divergence acts as a friction on Western efficiency. While Chinese plants can process high-grade mixed concentrates, Western plants must often spend energy and capital cleaning their feed to meet low RAD thresholds before processing can even begin. New technology deployment: AI Cascades versus Western validation. As the West attempts to catch up, it is betting on step-change technologies to leapfrog the established Chinese mixer-settler technology. Meanwhile, China is not standing still. It is optimizing its existing infrastructure with advanced computation, creating a moving target for Western competitors. While often viewed as a brute force industrialist, the Chinese rare earth sector is aggressively deploying artificial intelligence and machine learning to optimize solvent extraction. The SX process involves hundreds of mixer-settler stages, each with variables for pH, flow rate, extractant concentration, and temperature. Controlling this equilibrium manually is difficult. Doing it dynamically to maximize recovery and minimize reagent use is a perfect use case for AI. Recent Chinese industrial research highlights the use of improved differential evolution algorithms, such as LCT-ADE, to model the effective separation coefficients in real time. These models account for the efficacy of the agitator and non-ideal mixing conditions that theoretical models miss. By digitizing the extraction cascade, Chinese operators can squeeze an extra 0.5% to 1% recovery out of the system. At the scale of 50,000 tons per annum, a 1% efficiency gain translates to millions of dollars in pure profit and hundreds of tons of additional strategic oxide. This AI cascade represents a hidden efficiency gap. The software running Chinese plants is likely years ahead of the PID controllers used in nascent Western facilities. The integration of digital twins for their SX plants allows Bao2 to simulate process changes before implementing them, reducing the risk of downtime or off-spec product. The Western response is to change the hardware physics. Companies like Ucore Rare Metals and Rainbow Rare Earths are commercializing technologies that replace the vast footprint of mixer settlers with column-based or continuous ion exchange systems. Ucore's Rapid SX technology utilizes column-based solvent extraction. Unlike mixer settlers, which rely on gravity settling, requiring large surface areas and long residence times, Rapid SX uses rapid kinetics within a column to achieve separation. Ucore claims this results in processing speeds up to 3 times faster than conventional SX, with a significantly reduced physical footprint. This reduction in footprint is not just a real estate saving. It reduces the work-in-progress inventory, the amount of expensive dissolved rare earth locked up in the plant pipes at any given time. However, this technology is still in the commercialization/demonstration phase, for example, the Strategic Metals Complex in Louisiana, whereas Chinese mixer settlers have decades of operational data. The challenge for Ucore is proving that their faster kinetics do not come at the cost of separation selectivity or long-term operational stability. Rainbow Rare Earths is deploying continuous ion exchange for its Phalaborwa project in South Africa. Processing phosphogypsum, a waste product, Rainbow uses CIX to reject impurities and concentrate the rare earths before a simplified SX circuit. They report reductions in residence time from 32 hours to 8 hours, and a reduction in filter requirements from 7 units to 2. This efficiency is derived from the specific chemistry of their feedstock and the use of proprietary ion exchange resins. The efficiency gap here is paradoxical. The West has potentially superior technology on paper, faster kinetics, smaller footprint, lower inventory. However, China has proven technology at scale. The risk for Western projects is the validation gap, taking a pilot plant success and making it work at 4,000 tons per annum without unexpected chemical scaling issues. China's efficiency is boring but reliable. The West's efficiency is revolutionary but risky. Until technologies like Rapid SX and CIX run at commercial nameplate capacity for several years, the efficiency gap remains defined by China's operational certainty versus the West's technological promise. Global metallization capacity, the furnace gap, and purity standards. If separation is the bottleneck, metallization is the choke point. Rare earth oxides are useless for magnet manufacturing until they are converted into rare earth metals, or alloys. This process involves high-temperature molten salt electrolysis, a notoriously energy-intensive and finicky process that is currently the weakest link in the non-Chinese supply chain. China produces approximately 94% of the world's rare earth magnets, which implies a near total lock on the metallization step. The operational reality of Chinese metallization is characterized by massive electrolytic cell halls operating on subsidized industrial electricity. The efficiency here is thermal and electrical. Keeping thousands of pots at 1,000 degrees Celsius requires a stable, cheap baseload power supply, which China's coal-heavy grid provides. The utilization rates of these furnaces are kept high to maintain thermal equilibrium. Shutting down a pot line is expensive and damaging to the cells. Crucially, China uses this dominance to set the rules of the road for purity. The Chinese national standard, GB-T, for rare earth metals, dictates the allowable limits of impurities like carbon, oxygen, and iron. By controlling the standard, China effectively controls the merchant market. Western producers attempting to sell metal into the global supply chain must meet these Chinese specifications or the stricter ASTM standards demanded by Western defense contractors. The disparity between GB-T and ASTM standards can act as a non-tariff barrier. Chinese metals are optimized for their domestic magnet industry, while Western metals often have to prove super purity to justify their higher price point. The Chinese standard is often designed around the specific impurities found in Chinese ore, meaning Western producers with different impurity profiles, e.g. higher calcium or magnesium, may struggle to meet the GB-T spec without additional expensive purification steps. Outside of China, metallization capacity is scant. Neo Performance Materials stands as the primary exception. Their Silmet facility in Estonia is the only commercial-scale rare earth separation plant in Europe, and they are vertically integrating into magnet manufacturing with a new plant in Narva. Neo's efficiency lies in its heritage. The Silmet plant was a Soviet-era uranium and rare earth facility, meaning it has the legacy infrastructure and institutional knowledge similar to Baotao, albeit on a smaller scale. Neo produces approximately 2,000 to 5,000 tons per annum of magnets, a strategic but small volume compared to Chinese output. Their metallization capacity is integrated with their separation plant, allowing for hot transfer efficiencies and tight quality control. Vietnam is emerging as the metallization backup. With the world's second-largest rare earth reserves, Vietnam is attracting investment from South Korean firms like LS Eco Energy to build metallization capacity. However, these projects are largely in the pilot stage, with recent investments around $19.3 million. The technical challenge in Vietnam is replicating the tacit knowledge of Chinese furnace operators. Electrolysis is as much an art as a science. Maintaining cell efficiency and preventing anode effect, a disruption in the electrolysis process, requires experienced labor that Vietnam is currently training, likely with Korean or covert Chinese assistance. The furnace gap is arguably the widest technical chasm. While the West is building oxide separation plants, MP, Lynas, and Arafura, it has largely neglected the metallization step. Without domestic metallization, Western oxides must be shipped to China or Vietnam or Thailand for conversion, negating the strategic goal of supply chain independence. Southern China Standard versus Western HREE projects. The discussion of efficiency must bifurcate between light REEs, NdPr, and heavy REEs, DyTb. China's dominance in HREEs is not just industrial, it is geological. The efficiency gap here is determined by the fundamental difference between extracting ions from clay versus extracting atoms from crystal rock. Southern China's ion adsorption clays are a geological anomaly. In these deposits, rare earths are adsorbed onto clay minerals in an ionic state. This means they do not need to be cracked with high temperatures or aggressive acids. They can be extracted using in situ leaching with ammonium sulfate solution. The operational reality is remarkably simple. Drill holes into the mountain, inject ammonium sulfate, and collect the pregnant leach solution at the bottom. This process avoids the energy-intensive comminution, crushing, grinding, and roasting steps required for hard rock mining. The efficiency is high in terms of OPEX and CAPEX. No crushers, no mills, no kilns. However, the environmental efficiency is catastrophic. This method has historically caused severe soil erosion, groundwater contamination with ammonia and heavy metals, and landslides. China has tightened environmental regulations, banning surface mining of clays in favor of in situ leaching and cracking down on illegal mining. Yet the fundamental economic advantage remains. Chemically, it is far easier to wash ions off a clay particle than to tear them out of a crystal lattice. This geological efficiency sets a price floor for HREEs, dysprosium and terbium, that hard rock miners struggle to match. The cost of producing a kilogram of dysprosium from clay is structurally lower than from hard rock, provided environmental externalities are ignored or managed cheaply. Western attempts to produce HREEs focus on hard rock minerals, primarily xenotime. Northern Minerals' Browns Range and Arafura's Nolans are the leaders here. Northern Minerals' Browns Range project relies on the Wolverine deposit, a xenotime ore rich in dysprosium and terbium. The processing flow sheet requires crushing, grinding, magnetic separation, and flotation to produce a 25% TREO concentrate, followed by a sulfation bake, acid roast, to crack the xenotime. To get HREEs from Browns Range, one must mechanically pulverize rock and roast it at 300 degrees C+ with concentrated acid. To get HREEs from southern China, one effectively waters the hill with fertilizer, ammonium sulfate. The energy and reagent intensity of the Western hard rock route is orders of magnitude higher. This physics dictates that Western HREE projects will always have a higher base cost than Chinese clays. Western projects compete on ESG efficiency. Manufacturers like Siemens or Tesla may pay a premium for HREEs that did not involve injecting ammonia into a watershed or displacing villages. And Western projects like Arafura are designing ore-to-oxide single sites, attempting to recapture the logistics savings that Baotou enjoys. Arafura's Nolans project includes a phosphoric acid byproduct stream, which helps subsidize the rare earth production. This polymetallic approach, extracting value from the phosphate as well as the rare earths, is a necessary strategy to close the economic gap with the cheap, dirty geology of southern China. Without such byproducts, standalone hard rock HREE mines face a daunting economic battle. Asymptotic Pursuit. The investigation into operational realities of Chinese SOEs versus emerging Western processors reveals a landscape where the gap is dynamic, multidimensional, and structurally entrenched. In the realm of light rare earths, NdPr, the gap is closing. MP Materials and Lynas have demonstrated that Western companies can achieve operational stability and profitability. Their recovery rates and production volumes are becoming competitive with Chinese standards, albeit with higher environmental compliance costs and less integrated chemical ecosystems. The operational efficiency of Lynas's separation circuits and MP's beneficiation improvements suggest that the West can compete on cost for LRREs if fair market conditions exist and if they can continue to optimize their reagent consumption. In the realm of technology, the gap is divergent. China is optimizing the status quo, using AI and digital twins to squeeze maximum efficiency out of proven mixer-settler technology. The West is attempting to disrupt the status quo with Rapid SX and CIX, accepting higher technical risk for potential footprint and inventory savings. This is a gamble. If the new technologies work as advertised, the West could leapfrog China in capital efficiency. If they stumble, the West remains years behind. In metallization and heavy rare earths, the gap remains a chasm. The lack of Western electrolysis capacity and the fundamental geological disadvantage of hard rock HREE mining versus Chinese ionic clays means that for the most critical elements, DYTB, and the final value-add steps, metal and alloy, the West remains dangerously dependent. The technical efficiency gap is not merely a matter of better pumps or smarter software. It is a structural gap defined by China's 40-year head start in creating an integrated industrial ecosystem where mining, separation, metallization, and magnet manufacturing feed into one another. Western projects are islands of efficiency in a disconnected sea. Chinese SOEs are a continent. Closing the gap requires not just efficient factories, but the reconstruction of the entire industrial archipelago that supports them. Corporate solvency, M&A, and the processing gap. The global rare earth element (REE) sector has arrived at a moment of profound structural bifurcation in the mid-2020s, a period defined by the collision of Western geopolitical ambition with the unyielding mathematics of chemical engineering and capital efficiency. As the world transitions through 2026, the narrative of decoupling from Chinese supply chains has moved from policy rhetoric to the hard reality of balance sheets, revealing a landscape littered with capital inefficiencies, technical bottlenecks, and a solvency crisis among junior miners that threatens to undermine the strategic objectives of the United States and its allies. For the past decade, the prevailing thesis in Western capitals was that capital infusion alone could bridge the processing gap, the dearth of refining capacity outside China. However, a forensic examination of the sector in 2025 and 2026 demonstrates that money is not the sole constraint. Rather, it is the interplay of technical expertise, operational expenditure, OPEX, parity, and the sheer velocity of Chinese state-directed consolidation. While Western governments have begun to deploy capital through vehicles like the U.S. Department of Defense, DoD, and Export Finance Australia, EFA, the financial health of the recipients varies wildly, creating a two-tier market, a strategic sphere of government-backed incumbents and a commercial sphere of distressed juniors facing liquidation or predation. This part executes an exhaustive financial and operational assessment of the key non-Chinese players, MP Materials, Lynas Rare Earths, Iluka Resources, and Neo Performance Materials, and contrasts their funded resilience against the precarious state of the junior market. It further deconstructs the refining margins that keep Western projects on the edge of viability, analyzes the emerging M&A dynamics driven by Chinese state-backed aggregators versus Western defense funds, and scrutinizes the legal reality of offtake agreements that underpin the sector's debt financing. Incumbents, a financial and operational assessment. The non-Chinese rare earth value chain is not a monolith, but a fragmented archipelago of projects anchored by four primary entities. Each represents a distinct stage of maturity, yet all share a common vulnerability: the struggle to achieve cost parity with Chinese producers who benefit from integrated supply chains, state-subsidized reagents, and legacy infrastructure. MP Materials, the operator of the Mountain Pass mine in California, stands as the vanguard of American rare earth independence. However, the company's financial trajectory throughout 2024 and 2025 illustrates the severe pivot penalty incurred when transitioning from a simple mining operation to a vertically integrated chemical processor and magnet manufacturer. A granular analysis of MP Materials' balance sheet reveals a significant escalation in leverage, a direct consequence of its aggressive CapEx deployment for Stage 2, refining, and Stage 3, magnet manufacturing. In the fiscal period ending September 30, 2025, MP Materials reported long-term debt of $0.93 billion. While this figure represents a stabilization, a marginal 0.84% decline year-over-year, it sits atop a dramatic 33.25% surge in debt load observed in 2024, where liabilities jumped from $0.682 billion to $0.909 billion. This accumulation of debt correlates precisely with the capital-intensive construction phases that have strained the company's free cash flow. The transition has fundamentally altered the company's risk profile. In previous years, MP Materials operated as a high-margin exporter of concentrate. By 2025, the cessation of concentrate sales to China, a strategic necessity to feed its own refineries, severed its primary revenue artery. In the third quarter of 2025, consolidated revenue declined 15% year-over-year to $53.6 million, resulting in a net loss of $41.8 million. This loss was not a function of geological failure or operational mismanagement, but a deliberate strategic contraction. The company stopped selling low-margin rare earth concentrate to third parties, primarily Chinese refiners like Shanghai Resources, in July 2025. This decision, while strategically sound for the long term, created a massive revenue vacuum, causing the materials segment revenue to plummet by 50%. The operational strain of this transition is evident in the deterioration of cash flows. Free cash flow stood at a negative $114 million in the first half of 2025, following negative free cash flows of $196 million and $173 million in 2023 and 2024, respectively. This persistent cash bleed reflects the reality of the processing gap. Producing separated oxides is exponentially more expensive and technically difficult than mining concentrate. The cost of goods sold, or COGS, nearly doubled in 2024, rising to 94% of revenues compared to just 37% the prior year. This metric alone encapsulates the immense challenge of Western refining. The margins that exist in mining evaporate when confronted with the OPEX of chemical separation in a Western regulatory environment. However, standard solvency analysis fails when applied to MP Materials because it does not account for the sovereign put option provided by the U.S. government. Recognizing that market forces alone would likely bankrupt a Western refiner competing with China, the DoD has effectively insured MP Materials against market collapse. The DoD's 10-year price protection agreement establishes a floor of $110 per kilogram for neodymium-praseodymium products. This intervention is the single most critical data point in the company's solvency profile. With prevailing Chinese market prices often languishing in the $50–60 range, the $110 floor guarantees gross margins that the open market would deny. Furthermore, the DoD has injected $400 million into the company's equity and provided low-interest financing to support heavy rare earth separation. Combined with a $500 million prepay agreement with Apple for magnets starting in 2027, MP Materials operates with a safety net that mitigates traditional bankruptcy risk despite its negative free cash flow. The Stage 3 magnet facility in Texas, expected to commission in 2028, with capacity ramping from 1,000 to 10,000 tons, represents the final leg of this subsidized journey. Without this state backing, MP Materials' current debt-to-equity ratio of 0.90 and negative operating margins would signal high distress. With it, they signal a strategic asset in a build phase. Lynas Rare Earths, as the only commercial-scale producer of separated rare earths outside China for over a decade, serves as the operational benchmark for the sector. Yet its recent history is defined by the massive capital expenditure overruns at its new Kalgoorlie cracking and leaching facility, a project necessitated by political pressure in Malaysia rather than pure economic logic. The Kalgoorlie facility was designed to mitigate geopolitical risk by moving the radioactive cracking and leaching phase, where monazite ore is dissolved, from Malaysia to Western Australia. The project has become a cautionary tale regarding the inflationary pressures facing Western infrastructure projects. The capital cost estimate for Kalgoorlie was revised upward to $800 million in 2024, a staggering $300 million increase from the original $500 million budget. A review of the project's development reveals that these overruns were driven by a confluence of labor shortages in the Western Australian mining sector, global material cost inflation, and unforeseen technical complexities. Specifically, the necessity for enhanced electrical backup systems following regional grid failures and extended commissioning timelines contributed to the blowout. Despite these challenges, the facility commenced production of mixed rare earth carbonate (MREC) in the June 2024 quarter, feeding the Malaysian separation plant. Despite the Kalgoorlie cash drain, Lynas maintains a robust balance sheet relative to its junior peers. In mid-2025, the company successfully executed a $750 million institutional placement. This liquidity injection was critical, ensuring that the company could absorb the Kalgoorlie overruns without breaching debt covenants or stalling its towards 2030 expansion strategy. The company's ability to raise such capital attests to its status as a proven operator, a distinction that separates it from the speculative junior market. Technologically, Lynas has achieved a pivotal milestone in the separation of heavy rare earth elements, HREE. In mid-2025, the company produced its first commercial batches of separated dysprosium, Dy, and terbium, Tb oxides at its Malaysian facility. This development effectively breaks the absolute Chinese monopoly on HREE processing, which stood at 99.9% prior to this achievement. The new HREE facility in Malaysia is targeted to process 5,000 tons per annum of feedstock, with a capex of approximately $180 million. While this volume is modest compared to China's dominant output, it represents the only viable non-Chinese supply chain for the essential additives required for high-temperature magnets in defense and EV applications. Operational data from 2024 and 2025 indicates a recovery in production volumes following the Malaysian licensing disruptions. In the quarter ending June 2025, Lynas achieved NdPr production of 2,080 tons, exceeding the 2,000-ton threshold for the first time. Total REO production reached 3,993 tons in the September 2025 quarter, up significantly from 2,722 tons the previous year. This ramp-up suggests that the mechanical bottlenecks of the new Kalgoorlie feed system are being resolved, positioning Lynas to capture market share as demand rebounds. Iluka Resources, traditionally a mineral sands miner, is attempting one of the most ambitious pivots in the sector: the construction of a fully integrated rare earth refinery at Inaba in Western Australia. However, the project has been plagued by severe cost escalations that threaten its commercial viability without deep government subsidization. The Inaba refinery was initially sanctioned with a capital budget of $1.2 billion. By late 2024 and into 2025, estimates had ballooned to between $1.7 and $1.8 billion. This escalation forced Iluka to return to the Australian government for a bailout, resulting in a funding package that involves a non-recourse loan from Export Finance Australia, or EFA, totaling over $1.25 billion, plus an additional $400 million risk-sharing arrangement agreed upon in late 2024. An analysis of Iluka's half-year 2025 results shows a company financially bifurcated between a struggling mineral sands business and a capital-hungry rare earths division. Net debt for the rare earths business stood at $338 million, while the mineral sands division held net debt of $164 million. The project relies entirely on the EFA non-recourse loan structure. Without this sovereign shield, the project's internal rate of return, IRR, would likely fail commercial hurdles. Iluka estimates that even under optimistic scenarios, the refinery's equity IRR ranges widely from 35% to 51%, but these figures are predicated on government support capping the downside risk. The delay in commissioning to 2027 leaves a significant window where Iluka is deploying massive capital, $196 million in H1 2025 alone, without generating rare earth revenue. The strategic rationale for Inaba lies in its ability to process both light and heavy rare earths, specifically the monazite and xenotime stockpiles at Inaba, potentially making it a strategic hub for third-party feedstocks like those from Northern Minerals. Neo Performance Materials occupies a unique niche as a processor rather than a miner, leveraging its Solvent facility in Estonia. Unlike the miners struggling with extraction and cracking, Neo focuses on separation and magnet manufacturing, a strategy that has shielded it from some of the mining-specific risks but exposed it to feedstock vulnerabilities. In 2025, Neo inaugurated Europe's first industrial-scale sintered NdFeB magnet plant in Narva, Estonia. The facility is designed for an initial capacity of 2,000 tons per annum, scalable to 5,000 tons. Financially, Neo demonstrates a more stable, albeit lower margin, profile than the prospective miners. In Q2 2025, the company reported revenue of $114.7 million and an adjusted EBITDA of $19 million, raising full-year guidance to $64 to $68 million. Notably, Neo's CapEx discipline has been superior to its upstream peers. Phase 1 of the Narva plant cost approximately €75 million, a fraction of the capital deployed by MP or Lynas for upstream facilities. This suggests that the midstream to downstream segment may offer superior returns on capital employed, or ROCE, compared to the capital-intensive upstream sector, provided feedstock can be secured. Neo's strategic vulnerability lies in feedstock. Historically dependent on Russian and Chinese concentrates, it is aggressively diversifying through partnerships with Energy Fuels and potentially Australian miners. The company is constructing a pilot HREE separation line at Silmet to process dysprosium and terbium, aiming to reduce reliance on Chinese separation for these critical magnet inputs. The deal with Energy Fuels to process monazite from the White Mesa Mill in Utah represents a critical transatlantic supply chain link, attempting to bypass China entirely. Junior miners' solvency crisis, balance sheets, and burn rates. Beyond the funded incumbents lies a valley of death for junior miners, characterized by rapidly deteriorating balance sheets, high debt service costs, and the inability to raise equity without catastrophic dilution. The market has bifurcated into those with sovereign backing and those facing insolvency. Hastings Technology Metals, developing the Yangibana project, exemplifies the acute distress in the sector. By mid-2025, the company faced significant questions regarding its going concern status. Financial reports show a net loss of $222 million for the year ending June 2025, with a cash burn that depleted reserves to critical levels. The company's debt load is alarming. As of June 2025, it carried $128.7 million in debt against only $10.8 million in cash, resulting in a net debt position of $117.9 million. with liabilities due within 12 months totaling $130.1 million. Hastings is technically reliant on continuous refinancing or equity injections to survive. To stave off insolvency, Hastings has resorted to selling non-core assets, specifically divesting its gold assets to Metal Bank Limited for share consideration. This asset stripping is a classic sign of a company in distress, sacrificing long-term optionality for immediate liquidity. The Yangibana project's capex has been revised, but the company's inability to secure full project financing in a high interest rate environment has left it vulnerable to predatory M&A or administration. Arafura Rare Earths, developing the Nolans project, has managed to secure funding, but at the cost of massive shareholder dilution. The Nolans project, requiring over $1 billion in capex, has attracted a complex web of sovereign debt guarantees from Export Finance Australia, Export Development Canada, and Euler Hermes, Germany. However, debt requires equity. In late 2025, Arafura executed a $475 million capital raise at $0.28 per share, resulting in a 35% to 40% dilution of existing shareholders. While this successfully removed the immediate insolvency risk, leaving the company with pro forma cash of $634 million, it highlights the extreme cost of capital for Western rare earth projects. The entry of Hancock Prospecting, Gina Reinhardt, as a cornerstone investor suggests that deep-pocketed private capital is now required to bridge the gap that public markets are unwilling to fund. The Nolans project is now fully funded, but the equity story has been reset, with original shareholders absorbing significant value erosion to ensure the project's survival. VHM Limited, developing the Goshen project, provides a crucial insight into the failure of the China partner model. In early 2026, VHM terminated its binding offtake agreement with Shenghe Resources, citing unmet conditions. While publicly framed as a move to maximize optionality and engage with Western partners, forensic analysis suggests this was a forced pivot. The strict US and Australian regulations regarding Chinese involvement in critical minerals likely made the Shenghe deal a poison pill for securing Western debt financing, such as from EFA or US Exim Bank. VHM is now aggressively courting Western credit export agencies, having received letters of support from US Exim for up to $200 million. The termination allows VHM to market 100% of its product to Western off-takers, potentially unlocking premium pricing, but it leaves the project without a secured revenue stream in the interim, heightening its risk profile until new binding agreements are signed. The acquisition of Peak Rare Earths by Shenghe in late 2025 is the definitive case study of Chinese aggregation. Shenghe acquired the Tanzanian Nagwala project for $195 million, a valuation that represents a fraction of the project's net present value. This acquisition secures high-grade feed for Shenghe's processing facilities in China, effectively removing a major non-Chinese asset from the Western supply chain. The transaction highlights the speed and certainty of Chinese capital compared to the conditional, bureaucratic pace of Western funding. While Western entities dithered over ESG and debt terms, Shenghe executed an all-cash takeover. Processing gap, refining margins and cost parity. The central economic thesis of the Western rare earth industry, that it can compete with China on cost, is structurally flawed without state intervention. The processing gap is not merely a lack of infrastructure, it is a chasm in refining economics. Analysis of refining margins reveals a persistent structural disadvantage for Western producers. Integrated Chinese producers operate with neodymium-praseodymium oxide production costs estimated between $35 and $50 per kilogram. In contrast, Western greenfield projects require incentive prices in the range of $75 to $105 per kilogram to achieve commercial viability. This divergence, often referred to as the China price, is driven by three structural factors. First, Western projects like Linus's Kalgoorlie and MP's Stage 3 are seeing capital intensity of $200 to $300 per kilogram of annual capacity, nearly double the historic Chinese benchmarks. Second, while Chinese standards have tightened, legacy infrastructure and state-subsidized waste management continue to lower effective OPEX. Third, the 13% VAT rebate on exports and direct state subsidies for solvent extraction reagents depress Chinese operating costs below Western floors. Currently, Chinese NdPr oxide prices hover around $60 to $65 per kilogram, a level that renders most Western projects unprofitable without the premium pricing floors, like the DoD's $110 per kilogram. The bottleneck is most acute in heavy rare earths. Solvent extraction remains the dominant technology, requiring hundreds of mixer-settler stages to separate elements with adjacent atomic numbers. China controls 99.9% of global heavy rare earth separation capacity. Western attempts to replicate this are nascent. Linus's new Malaysian circuit is the only commercial non-Chinese heavy rare earth facility, but its capacity, 5,000 tons feedstock, is a fraction of global demand. Iluka's Enaba refinery is designed to process heavy rare earths, but is years from commissioning. Innovative technologies like continuous ion exchange or chromatography are being piloted by companies like Ucore and Meteoric, but they have not yet been proven at the scale required to displace Chinese SX dominance. The processing gap for dysprosium and terbium is effectively absolute until at least 2027-2028. The implications of this gap are severe. Market forecasts indicate a massive deficit in dysprosium and terbium, critical for high-temperature magnets. By 2035, the global deficit for dysprosium oxide is projected to reach 2,920 tons. Western mines are forecast to meet only 29% of heavy rare earth demand outside China by 2035. Prices for dysprosium in Rotterdam have traded at $900 per kilogram, nearly triple the domestic Chinese price of $255 per kilogram, illustrating the bifurcation of the global market. M&A dynamics, predators, prey, and valuation gaps. The disconnection between asset value, resources in the ground, and equity value, share price, has created a fertile environment for M&A, characterized by two distinct predatory species: Chinese state-backed aggregators and Western strategic capital. The Shanghai and Peak transaction demonstrates the Chinese strategy: acquire distressed Western assets at a discount to secure feed. Shanghai's acquisition of Nongala was driven by the need to feed its own refineries, bypassing the Western desire for independent supply chains. This trend poses a significant threat to Western resource security, as Chinese firms can offer immediate liquidity that Western markets often deny to juniors. Conversely, Western mining majors like BHP and Rio Tinto have remained largely on the sidelines of direct rare earth M&A. Their focus in 2026 has been on the consolidation of Pilbara iron ore operations to drive efficiency and unlock 200 million tons of additional resource through shared infrastructure. The complexity and small scale of the rare earth market compared to copper or iron ore make it unattractive for direct entry by the majors. Instead, the defense funds, like Orion Resource Partners and Strategic Family Offices, are the active acquirers. Hancock Prospecting's entry into Arafura and Brazilian rare earths signals that Australian domestic capital is stepping in. M&A targets trading well below book value include Hastings Technology Metals due to distress and potential take-private candidates if financing stalls. The valuation gap for these juniors, trading at 0.2x to 0.3x NPV, make them prime targets for consolidation into a Western champion entity, possibly orchestrated by government-backed funds to prevent Chinese capture. Brazilian frontier, a new cost paradigm. Brazil has emerged as the most significant disruptive force in the rare earth sector, offering a geological alternative that could theoretically undercut Chinese costs: ionic adsorption clays. The rise of meteoric resources, Caldera Project, and Brazilian rare earths, Monte Alto, shifts the focus from hard rock monazite like Mount Wed and Mountain Pass to IAC deposits. These deposits allow for rare earths to be extracted using simple ammonium sulfate leaching at ambient temperatures, eliminating the energy-intensive cracking and roasting phases required for hard rock. An assessment of Meteoric's Caldera project reveals operating costs estimated at $6.74 per kilogram of recovered total rare earth oxide, TREO, a figure that is competitive with the lowest-cost Chinese producers. The capital intensity is also significantly lower. Meteoric projects a capex of $403 million for a project of massive scale, compared to the $1 billion plus required for similar hard rock output. However, the Brazil discount applies. While Meteoric and Viridis secured preliminary environmental licenses in late 2025, the infrastructure deficits in Minas Gerais and the lack of domestic separation capacity mean these projects are currently dependent on exporting concentrate. The recent listing of Caldera in Brazil's Climate and Ecological Transformation Investment Platform, BIP, suggests strong state support, but the timeline to production remains contingent on environmental permitting and the construction of pilot plants to prove the metallurgical flow sheets. Offtake forensics, binding versus MOU. The quality of the order book differentiates the solvent from the speculative. In the current market, a Memorandum of Understanding, MOU, is effectively worthless for debt financing. MP materials, high quality, strategic. The General Motors and Apple agreements are binding commercial contracts. The Apple deal involves a $500 million prepayment, effectively acting as zero-interest working capital, while the DoD contract provides a price floor. Linus, high quality. Contracts with Japanese trading house JER and the US DoD provide floor price protection and capital injections. Arafura, mixed, hardening. The offtake with Hyundai Kia 1500 TPUA and Siemens Gamesa 1440 TPUA contains pricing mechanisms linked to market indices. The recent Traxys deal up to 300 TPUA adds a trader distribution channel. The transition from MOUs to binding offtakes was the prerequisite for their debt package. VHM, low quality, reset. The termination of the Shanghai deal leaves VHM with 100% uncommitted product. While they claim this maximizes optionality, in the eyes of a credit committee, it reduces the project's bankability to zero until replaced by a Western counterparty. The industry trend is shifting toward take-or-pay contracts with floor price mechanisms. The DoD's $110 per kilogram NdPr floor has set a precedent that other Western governments, Australia, EU, are under pressure to match to make projects like Inayaba and Yangibana bankable. The assessment of the non-Chinese rare earth value chain in 2026 reveals a market that has ceased to function as a unified global commodity system. It has bifurcated into two distinct spheres. The commercial sphere, dominated by China, characterized by subsidized costs, integrated supply chains, and predatory M&A activity, e.g. Shanghai, Peak. In this sphere, Western juniors cannot compete on a level playing field and face a high risk of insolvency or acquisition by the very competitor they were designed to displace. The strategic sphere, a unified government-guaranteed ecosystem where solvency is maintained not by market margins, but by sovereign intervention, DoD price floors, EFA non-recourse debt. MP Materials, Linus, and Iluka survive and expand only because they inhabit this sphere. For the investor and analyst, the processing gap is not merely a lack of centrifuges or solvent extraction tanks. It is a gap in capital efficiency that private markets refuse to bridge. Consequently, the sector's future belongs to those entities that have successfully secured the sovereign put option, while the remainder of the junior market faces a wave of consolidation, insolvency, or acquisition by the very competitor they were designed to displace. The realization of a resilient Western supply chain will depend less on geology and more on the willingness of Western governments to underwrite the premium required to sustain it.